Good morning. We have midterm 3 coming up here right away. And as we've done with the other midterms, what we want to do is take a look at some practice problems. The nice feature of these sample problems is that they've actually appeared on midterms from previous years, previous semesters. And so it does, in some sense, it kind of represents the types of problems that you might encounter. So you still want to be looking at your homework problems. You still want to be looking at the examples that we've looked at in class, in lecture. But now in addition to that, here are some sampler problems that we are going to take a look at today. So let's go ahead and take a look at those. Now, there was this first page here, I guess, that was kind of an example of what we're looking at. But let's go ahead and, so we got 2 of these, as we had before. So we've got 1 of these, we'll do that for the first hour, and then we'll take a break, and then we'll come back for the second hour of class, and take a look at another set of practice problems. So, first problem here is saying that we have a lens. So the lens has a focal length of 80 centimeters, so this seems pretty representative of what we've been looking at in class. Again, physics 3A and 3B, but 3B even more so. We're just looking at a lot of topics. So we're looking at a lot of different aspects of physics, trying to build that foundational understanding of a wide range of topics. And so we're going to start out here looking at light, kind of classical light, looking at things like lenses and such. And then we're going to start looking at the wave properties of light. What kind of interference effects do we see in light? And then we're going to move on. We've got a problem from the relativity chapter, so I think we're looking at maybe chapter 36 here. So it's chapters 33 through 38. And here we have a problem from relativity. And then here's a problem from one of the quantum physics chapters. So that's what we're looking at. Probably a couple of problems from the optics chapters, something maybe on classical light, something on interference effects of light, and then a couple of problems from the relativity and quantum mechanics chapters. So let's take a look at this first problem. We've got a lens. I'm writing down the information given. It says focal length of 80 centimeters, and it's used to create an image on a screen. Now, image on a screen means that the image is real. So the DI is going to be a positive number. And, I always end up just drawing kind of a diagram. When I'm reading a problem like this, I'm going to start putting together a diagram. Maybe I make some corrections or some additions to it as I go through the problem. But my guess is in looking at the homework problems and also in, as you're working through a midterm, for example, that's a pretty good problem-solving approach to come up with. And so what we've got is there's an object. So the problem is suggesting we have a real object and a real image, and it's also saying that we have a converging lens. I mean, they give us a positive value for that focal length. So it looks like what we've got here is probably that simplest of examples using a lens, and that would be a single converging lens where a real object is used, the lens is used to form a real image of a real object. So this is what my diagram looks like so far, and I'm already making some, writing down some things here. First of all, there's going to be an inversion. The image will be inverted relative to the object. So that's something to keep in mind. I'm expecting DO is going to be positive, DI is going to be positive. What other information was given here? So they did say the height of the object and the height of the image. So this is at 4 centimeters. Now they told us the image height is 8. They didn't put a minus sign on that. Now it's a little ambiguous about the image height. Everything else points to a real image and a real object. So if that's the case, then I'm going to put a minus sign in by hand because, you know, reasoning through the problem, there's got to be an inversion that's taking place. And very likely when they're talking about the image height, they're not really keeping track of the inversion with that. Okay, so that's my justification. Now, if you're on a midterm and you're just not sure, just ask the question. Don't hesitate to just, you know, come up and ask, what's going on here? Are we allowed to have an inversion? So if questions come up, ask those questions. Don't ask the questions. Okay, bottom line is go ahead and ask. So what I'm going to do now that I've determined my values for f and HO and HI is I want to come up with a set of DOs and DIs that match the focal length. What I know is that the DO and the DI are related to the focal length from this formula. 1 over DO plus 1 over DI is going to equal 1 over the focal length. Now, there's a couple different algebraic approaches here. The one I took was this. What I ended up doing was I got a common denominator. I multiplied this by DI times, I multiplied through by DO, DI, DF everywhere. And what that left me with was a DIF, DOF, DODI. And so here's the DODI. Now on this side I'm going to get an FDI plus an FDO, and then I rewrote that. So I could have inserted a couple more steps in that algebra, but I'm going from here to here by multiplying through by that common denominator. All right. Now from here what we need to do is say that the, again I'm using my diagram here to think about this. The ratio of DI to DO is going to match the ratio of HI to HO. So I can write DI is equal to minus the magnification times DO. Now the magnification here, HI over HO, is going to be minus 2. That comes from this expression right here. And so if I take the DI that I have here and substitute in this expression, now I have F times DO, I can factor out a DO, 1 minus M is equal to DO squared minus M. So I took the two DIs and substituted in this expression. Now I can eliminate one factor of DO, and what I'm left with is DO is equal to the focal length, M minus 1 over M. So that's kind of a handy formula to work from, right? And in this case, the M, let's think about this, the M was minus 2. This would give me minus 2 minus 1, minus 3, divided by minus 2, the minus signs cancel. So the DO needs to be 3/2 times the focal length. That would be 120 centimeters. Okay, so there's some minus signs in here, and you know, minus signs shouldn't be such a big deal, but it is easier to get mixed up. Myself, I run into this too. If there's more minus signs around, it's a little harder to keep track of things, so I'm stepping through this all carefully. And then every time I get an answer here, like this is 120 centimeters, then I look back at my diagram and think, is that reasonable? Now I know from, doing all the homework problems and such, that when I go from a real object to a real image, the object needs to be outside the focal point. And this is outside the focal point. So everything here so far checks out. The DO came out positive. It's bigger than a focal length. So I'm gonna move on. A DI needs to be equal to minus M times DO. The M was minus 2. So plugging into this gives me 240 centimeters. So it seems reasonable. I've got a focal length of 80. The object is outside the focal point on one side. The image is outside the focal point, well outside the focal point on the other side. I can put these two numbers back into this formula and it works. So I've checked it, I've kind of reasoned through this, and everything seems to be checking out okay. And if the DI is twice as large as the DO, that's going to give me a magnification of 2 with that inversion that comes from real object to real image. Okay, so I'm going to say this problem, the setup itself, real object to real image, one lens, is about as simple as it can get, but the things that they're asking here are a little more complicated because algebraically I had to go in and move, I had to switch around some of the formulas that I'm used to using. All right. Now in a problem like this, we are expected to go back and work from kind of the basic formulas that we've set out. In any case, in part, let's go back and see if we've answered all the questions. That's always what happens here, is I get caught up in the problem and then I think, oh, did I ever answer the question? How far is the screen from the object? Ooh, that's a trick question. Let's see. The screen is where the image is. The object is where the object is. That would be the combined DO and DI. That is going to be 360 centimeters. Okay, so I'm going to write that down. And then B says, how far is the lens from the object? All right, lens is here, object is here. Oh, that's DO. So I think this is the way it's supposed to work. I'm not supposed to ask you what's the object distance. I'm supposed to imagine this experiment sitting out on a table, kind of like what we did in lab, and go, okay, how far should the lens and the object be away from each other? And then I have to figure out, oh, that's the DO in my formulas. So the DO is 120. We calculated that earlier. C says, is the image upside down or is it right side up? Upside down meaning it's inverted. So the image is, there's an inversion. Let's say it that way. That's more general. Between the object and the image, there will be an inversion. They will be in opposite directions. So yes, there is an inversion. And then D says, draw a diagram. I always draw the diagram. And so D, I just said, oh, C above, there it is. So there's the diagram, and it didn't ask for a detailed diagram. I did get a ruler out. So I got a ruler out. I didn't mark the focal length. I could have done a little more detail. This is probably adequate on this problem. You'd probably get full credit if it looks like this. But it would, to really make sure, I should have put in a focal point. Focal point is here and here, right? And I got the ruler out anyway. I just forgot to mark them. So focal point here, and then for this problem, that one line through the center of the lens works just fine. That's adequate to see what's going on. Questions on this? So on this particular midterm, this is representing kind of all of chapters, I'm going to say all of chapters 32 and 33 get represented here. So chapter 32 also kind of fits in well with chapter 33. So many of the same items going on there. Let's see. What else was I going to mention? These are the starting points. So the formulas that we have derived, I'll include this. So the magnification is defined as HI over HO. Using some basic geometry, we showed that HI is to HO as DI is to DO. But then we had to put a minus sign in because of the sign conventions that we have adopted for these different values. And then here is the formula relating focal lengths with object and image distances. So I felt like, you know, these are the formulas I have to start from right here, and that's where I started from, and then I worked through the algebra, solving for everything else. So again, any questions on this, stop by, let me know. Let's see, on problem 2, it says we now on problem 2 are looking at a diffraction grating. So now we've moved on and we're looking at something out of chapter 34/35, where we're looking at interference effects. And so we had those first couple chapters on mirrors and lenses, and now we're looking at chapters dealing with interference effects. And the interference effect chapters that we've really focused on, we started out looking at two-source interference, and then we looked at what would happen if we had more than two sources of interference, and then we looked at different examples like thin films, interference and such. And then in chapter 35 we moved on and looked at diffraction, a different type of interference, and then we looked at multiple slit devices, which are called diffraction gratings, kind of a misnomer. And then we looked at polarization. So polarization got thrown in there at the end too. So don't forget about polarization as a possible topic that could show up. So here it says that we've built a diffraction grating, and we've built it in such a way that we can take the visible light spectrum. We're specifically interested in taking the visible light spectrum and having the 700 nanometer end of that spectrum, that red, so the red end of the spectrum, we want that to be spread out all the way to 90 degrees. So when it talks about maximally spread out, we're trying to get the largest angular separation through the first order spectrum of visible light. So, so let's bring out the formula. So the formulas we've derived for working with diffraction gratings, multiple slit devices, devices with many slits to them, we use the d sine theta m lambda. And I put a subscript of big R here to represent the red end of the spectrum. So I'm going to solve for D. I want to find out, that's what they're asking for, right? Okay, they're asking where will the blue end of the spectrum be, and to solve for that, I want to come up with a value of D. Now, I probably could use ratios here too, and that would be fine. I'm just going to flat out solve for D, because I'm a little curious. So I'm going to put in M for 1. It says it's the first order spectrum, and then 700 nanometers for the wavelength. Now I want this at 90 degrees, and the sine of 90 is just going to be 1. Oh look, what I want, if I want a wavelength of 700 nanometers to show up at 90 degrees, I want the distance between consecutive lines on the diffraction grating, consecutive slits, to be 700 nanometers. I just want that separation to match the wavelength that's going to show up at 90 degrees. Now that I know what D is, I can take that very same formula, flip it around for the blue end of the spectrum. Again, this is first order. So the M value here will continue to be 1. And when I solve this, when I take the inverse sign, I end up with 34.9 degrees. So that's a pretty good angular separation. It's saying that with this particular design for my diffraction grating, I can get the visible part of the spectrum to spread out over 55 degrees, right? I'm going to spread out from the blue end of the spectrum is going to show up at 35. The red end of the spectrum is going to show up at 90. That's a lot of separation. Now, the diffraction grating could still work into the infrared or into the ultraviolet. We wouldn't be able to see that, but we could build devices with sensors that would be able to measure that effect out into those regions. So, we've got A solved, and as kind of a bonus along the way, we solved for D. Now, B says, what are the number of lines per centimeter needed to produce this spread? So they're asking about, well, not directly the D value, but they're asking about 1 over D. So we saw this in lab, and we saw this in some of the other examples, I think, with the examples that we've looked at in class. The D value for a diffraction grating is the distance between consecutive etchings or consecutive lines in the diffraction grating. Now, rather than report diffraction gratings in terms of their D value, it's more common to have the diffraction gratings listed in terms of 1 over D. Now let's think about, what does this mean? When we say 700 nanometers, what we mean is that it's 700 nanometers per line. So every line that we have etched into the diffraction grating material is separated by 700 nanometers from the one right next to it, and that's got to be maintained. So that's what gives diffraction gratings their remarkable properties. If we can maintain very, very careful measurements of one line to the next, one etching to the next, that's what gives us this really powerful interference effect where everything lines up in a particular direction. So we get a really high intensity signal for a given wavelength in one direction, and then it drops off very rapidly. And that's what makes diffraction gratings work. So what I'm solving for here is 1 over D. That's going to give me one line for every 700 nanometers. And what they wanted this in terms of was units of lines per centimeter. Well, just like we did in lab, I think, what we can do is convert the nanometers into seconds. Now that would be a factor of 10 to the 7th. Centimeters are, there's 10 to the 2 centimeters in a meter, and there's 10 to the 9 nanometers. So 10 to the 9 divided by 10 to the 2 would be 10 to the 7. And the nanometers in this calculation will cancel out. I just make sure all these numbers go into my calculator, and it says 14,290 lines per centimeter. That's remarkable, right? So that's some very careful etching that needs to be done in that diffraction grating material in order to maintain lines that are 14,290 lines per centimeter. Centimeters are not that big, and I'm trying to fit 14,000 etchings into them. Now, part C of the problem, so A and B I think we've got down. If you guys have questions, let me know. C says, this is kind of off by itself. It's almost a separate question. It says that we will always have the first and second order spectrum for visible light will always have a gap between them. However, the second and third order spectrum will always have a region of overlap regardless of the number of lines. So what this is suggesting is this. Let's come and take a look at this diffraction grating. Let's dial down the lines per centimeter. So if the lines per centimeter go down, if the D value goes up, then what's going to happen is this first order spectrum, both theta blue and theta red, are going to decrease. And what we'll see up here is the possibility of a second order spectrum, and maybe a third order spectrum that we could look at. So now, we don't know the specific value of D, but what we can do is we can write down this formula right here. So what I'm going to say is that when m is equal to 1, the blue end of the spectrum, sine of that angle, will be at 400 nanometers divided by whatever the D value is. So again, we're now talking about any diffraction grating at all. Any diffraction grating, any value of D. Now, the wavelengths of visible light, we're imagining, to be run from 400 to 700 nanometers. So what this is really coming down to is, how are the numbers 400 and 700 related to each other? And 700 is almost twice as large as 400, but not quite. So it's saying that the ratio of the red wavelength and the blue wavelength is less than 2. And because of that fact, what we can say is, well, for m equals 1, this is how we would go about calculating the angles at 400 and 700 nanometers. Now, if I move on to m is equal to 2, then in my formula, instead of a 1, I've got a 2. So instead of 400 nanometers, that's now 800. And instead of 700 nanometers, I've got 1400. Now again, we don't know the particular value of d, but what this formula shows, 700 over d will always be smaller than 800 over d. So that says, if I'm thinking in terms of these two angles, this angle that we solve for here will always be smaller than that one. That's going to create a gap between where the red end of the spectrum 1 ends and the blue end of spectrum 2 begins. There will always be a gap, and that's because the ratio of the wavelengths of light are less than 2. Now, what about the third order spectrum? Well, for the third order spectrum, the blue light will start again at 400 nanometers, but now I've got a factor of 3. So in my formula, 3 times 400 is 1200, and 3 times 700 is 2100. Now, 1400 is bigger than 1200, so that says that the angle at which the red end of the spectrum for the second order spectrum, the angle that that finishes at, will be larger than where the third order spectrum begins. And so there's always going to be some overlap between second and third order spectra. If we're looking at the full range of the visible spectrum, then we'll always have red overlapping with blue between second and third order. And again, it just has to do with the ratios. If this were, what would we need here? If this were a little smaller, right? What we would need is, boy, I have to think about that. So we're going from 400 to 700 and then 800 to 1400. For 1200, if we scale this down, if this wrapped up at 600 nanometers, this would be at 1200, and that would mean that the two would be lined up just barely. So if I wanted the third order spectrum to be distinct from the second order spectrum, we would want the wavelength here to be no more than 3/2 of the 4. Anyway, what we wanted to be able to do with this problem is show that if we're going to use the whole entire visible spectrum from blue to red, we really should focus in on the first order spectrum. Because if we're looking at the second order spectrum, there's a possibility we're going to pick up some of these other, part of the third order spectrum is going to overlap with the second order spectrum. There'll be both of those showing up at the same location on our screen. All right. Any questions on that, let me know. Let's move on and take a look at this third example. Okay, so we've looked at light, lenses, and then interference effects. Now we're looking at, well, this is coming from relativity. And relativity, we need to look at relativity. We found out that there are formulas from relativity that are going to make sure that we're getting the answers correct when we're moving on to atomic and nuclear physics and molecular physics. So this problem is actually dealing with just how space and time are related. How are distances and time intervals related for different observers? And what we want to come down to is just, I think the first thing we just have to put out there is the amount of time that passes will not be the same in different reference frames. So in general, the amount of time that passes in one reference frame between two events is not the same in other reference frames. So I drew both reference frames. Here is the Earth that they talk about and the planet, Earth and planet. And what they've told us is that the Earth and this distant planet, it's not so far away. It's in a pretty nearby star system. This is only 10 light years away. Now notice the units that I'm working with here, and we talked about this in class, is that I'm writing this as c times years. And that means that by writing it this way, I can look for factors of c that will actually cancel with my units of c. So that c in there is right now is just a unit in terms of light years. Now what they also tell us, that's in this reference frame. Now the amount of time that takes place here would come from taking L and dividing by V, but we haven't solved for V yet. So we can't solve for T, but what we can do is move over to the other reference frame. In the other reference frame, what's going to happen is we're going to have length contraction. If we think of any distances measured in the Earth-planet frame, and then move over to the frame of the spacecraft, the reference frame, what we're going to find is that any distance that was measured here is going to be shorter. So the distance between the Earth and this distant planet are going to be shorter. And they're going to be shorter by a factor of gamma. So just the same way we wrote T is equal to L over V here, we can write T prime in this other reference frame. The time that passes here between the events is equal to the distance between the events divided by the speed. Now, L prime I don't know, but I can write that as L over gamma. So what that gives me is T prime is equal to L over gamma times V. And L was given and T prime was given. So they gave me the distance here in this reference, but they gave me the time in a different reference frame, in the reference frame of the spacecraft, where the spacecraft is at rest and the Earth and the planet are zipping by at some really, really high speed. So this is the formula I want to work from. And so I wrote these down. This is the information given. This is the formula I want to work from. So what I did is I'm not going to be solving for V, at least not right away. I'm solving for gamma times V. And that makes the algebra a little more involved. Gamma and V, if I know V, I can solve for gamma. If I know gamma, I can solve for V. They're two different variables that tell me how fast I'm going. V is directly in meters per second. Gamma is a little more subtle, but gamma also we've found to be a very useful variable to work in terms of. In fact, I always suggest that rather than try and solve for V directly, almost always, I'm going to say 85–90% of the time, it's easier to solve for gamma. Most often the algebra works out to be easier by solving for gamma instead of V. So let's try that. So here is gamma, here's my factor of V. What I'm going to do is I'm going to substitute in V written in terms of gamma. What we've shown in class is V is equal to C times 1 minus 1 over gamma squared square root. So I'll substitute that in. Now, what that needs to be equal to is L over T prime. So what we've got now is the T prime came down to here, the gamma times V came out here. I can take this formula, I can multiply through by gamma. Now gamma coming into here, that's going to give me a gamma squared because there's a square root sign here, and it's going to cancel out the gamma squared here. So bringing that factor of gamma in, gives me the expression gamma squared minus 1 square root. Now I took the factor of c and moved it to the other side into the denominator. So now I've got a formula that looks like this. I can plug in my 10 light years. I can divide through by c, divide through by 5 years. The years cancel the years. The c that was in light years actually cancels one factor of c. So by putting a factor of c building it into the units, it's built right into the units, when that variable shows up, I can cancel those out. So what I've got now is gamma squared minus 1 square root it's unitless, and it's equal to, numerically to 2.0 in this particular example. So in this particular example, it's just going to be a factor of 2. Now that makes sense in terms of units, because gamma doesn't have any units to it. All right, so let's solve for gamma. I'm going to square both sides. That becomes a 4, 2 squared, plus 1. The 1 gets carried to the other side. There's still a square root here. That means that gamma in this example is given by 5.0 square root. That's 2.24. When I solve for v, now that I know what gamma is, now I can flip that formula around and solve for v. It sounds a little crazy, but I'm going to repeat what I said before. Most of the time, 85–90% of the time, it's easier to solve the algebra in terms of gamma first, and then once I have gamma, go back and solve for v. Okay, so that's what we've done. We've solved for gamma, and now we're using our formula to go back and solve for v. And I came up with 0.8944. Now I know I'm carrying too many sig figs here. I apologize, but I have a hard time rounding off if it's 4, 5, or 6. I think, well, it's not really obvious one or the other. But so I kept an extra sig fig. No big deal. You guys know, I hope by now that you can get away with one extra sig fig. Part B then. We've got the v figured out, so that's it. That's my answer. So it took a lot of doing, but we got part A, and gosh, I hope B, C, and D aren't that hard. And fortunately, it looks like once A is solved, B and C come pretty quickly. So B now can be solved, which is the distance in this reference frame. How far away is the planet? Well, that would be L over gamma. That's only 4.47 light years away. So simply by coming up to speed, right, bringing this spacecraft up to this really, really high speed, that planet is not as far away. That star system is not as far away. It sounds crazy, but that's what happens as you start from Earth and you pick up speed, and by the time you are traveling at 0.8944 c, that planet that used to be 10 light years away is now only 4.47. Okay, and this effect is simply due to the way space and time are constructed. Okay, sounds crazy. The amount of time that it takes is going to be gamma times t prime, and I can take that value of gamma, 2.24, and that worked out to be 11.2 years. Now, how can I check numbers here? Well, I know that in the Earth frame, because the planet is 10 light years away, and because I can't travel faster than light speed, that it's going to take more years than the number of light years. So if it's 10 light years away, it's going to take me more than 10 years to get there. And 11.2 works out. I can plug back into these formulas and double check. And then in terms of the distance, well, how could I possibly get there in just 5 years? That would require that the distance be less than 5 light years. So everything seems to be working, I want to suggest. Now the last part of the problem is asking about Doppler effects. What's going to happen in terms of wavelength? This is something else that we derived in class. If objects are moving away from each other, the effect, if the distance between them is increasing, that's going to lead to wavelength that is what we call redshifted. And that's what's happening in this case. So the Earth, if we think of the Earth and planet as more or less representing some kind of a fixed coordinate system of our galaxy, then the spacecraft's motion, its speed that we've calculated, is relative to the Earth and that planet. And because of that speed, the signal that the spacecraft picks up is going to be redshifted. Plugging in the values for V, what was the value for V here? 0.8944 times c. And as we've been doing in our other examples, we want to write this velocity in terms of c. We don't want to write it in meters per second. We want to find out what fraction of c is the velocity that we need. And so plugging that into here, the c's all cancel out. This is going to become 1 plus 0.8944 divided by 1 minus 0.8944, and then we take a square root of the whole thing. That gave me a factor of 4.24, and that says that if I'm adjusting my radio receiver to pick up the radio transmissions from Earth, if I want to talk with mission control, then I need to tune this to 42.4 meters for the wavelength. I guess I could have written in what the frequency would be too. That would have been good to work in terms of frequency maybe. Now when the spacecraft turns around and heads back to Earth, that's going to create a blue shift effect, and that's going to flip the Doppler formula that we have. It's now going to be c minus v over c plus v square rooted, and that's going to give me 0.236 factor. And so now instead of, well, the signal was being sent out at what, 10 meters? So on Earth is using a signal of 10 meters. I think the people on Earth should adjust their transmission well, maybe not. It's probably easier for them than us. Anyway, the spacecraft has to adapt and now go looking for a signal with a wavelength of 2.36 meters. And again, I'm kind of thinking I should have put a frequency in for those. What would have been a frequency of the signal that you would tune to? Look at your FM radio signals and see if you can pick up that particular frequency. Questions on any of that? So there's another set of practice problems, and there's another problem involving relativity. The space-time stuff, I'm going to say, is kind of interesting to think about, and I mean, there are situations where it does become important, I guess. So I shouldn't say that it's not. When we get into nuclear radioactive decay and things like that, we'll see that if particles are moving really fast, their lifetimes are longer. They're going to survive longer, something we've already seen in the relativity chapter, and that's also going to be important to us. So this is important. Make sure that you understand how to work back and forth between different reference frames in terms of distances and time, passage of time. Let's move on to this last example now. So. And this is coming from the quantum physics chapter. And what we're asking about here is, it says we're looking at hydrogen, atomic hydrogen. It should say atomic. So we're looking, because it's not the same thing in molecular hydrogen. So let's just be clear about that too. Molecular hydrogen is not going to produce the same effects as atomic hydrogen. Now, we haven't really solved this energy formula correctly yet. I'm going to say that needs a square in it. So that's a correction I need to make. That needs to have a square. You guys picked that up right away, right? It should be n squared. The numbers I have here look correct. So I used the right formula, but I didn't get the square written. This is a formula that Bohr came up with, but as we talked about, Bohr's model has some serious errors in it. And so, but we're going to end up, surprisingly, when we do atomic physics, chapter 39, we're going to pick up right after the midterm, we're going to find out that full-blown quantum physics gives us the very same energy formula. Kind of remarkable that Bohr was able to come up with such a useful energy formula based on an incomplete model that had some serious flaws in it. We'll come back and do atomic hydrogen, what we're going to call the correct way, using the Schrodinger equation. In any case, these are the energies I wrote down from 1 through 7. So these are the different possible binding energies of the electron in atomic hydrogen. Individual atoms, not H2 molecules, but individual atoms of hydrogen. These are the possible energies of the electron quantum states. The possible energies of photons come from all the different ways that these are paired together. Now what I did is I went back and I added a few, 1 or 2 significant figures, because we're really down in this range. We're going to need these numbers too, and it would be nice to have a third significant figure. As those numbers are getting smaller and smaller, we're kind of losing some of the... I didn't write down as many as I should have here, so I rewrote it. Now for the visible part of the spectrum, which they're asking about in part A, the energy at the blue end of the spectrum, we can get that as hc over lambda. That would be 1240 eV nanometers over 400. That's 3.10 eV. At the red end of the spectrum, those photons have an energy of 1.77. So what I did first of all is, I'm thinking entirely in terms of energy. Energy is what gets conserved, not wavelength. Now I know there are those Rydberg formulas or something that the textbook is using. You know, I would encourage you guys to think in terms of energy first. Get everything solved in terms of energy conservation, and then the last step is to convert into wavelengths. So, and that's the way the problem is written up, too. So these are the possible energies of the electron. If we go from 3 to 2, 4 to 2, 5 to 2, and 6 to 2, the energies that we come up with by subtracting those values fall between 3.1 and 1.77. So let's think of the reasoning behind that. Anything dropping into state number 1, it's going to be too much energy. That's going to be at least 10.2 eV, and that's too much energy for visible photons. Visible photons need to be between 1.77 and 3.10. So the other possibility is, well, what about dropping into state number 2? Because if I look at the pattern of energies, state 1 is really, really deep. There's really a lot of binding energy there, 13.6. State number 2 is only 1/4 as much. So let's try those, and it turns out 3 to 2, 4 to 2, 5 to 2, 6 to 2, those 4 energies fall within the range of energies of visible photons. So 1.89, 2.55, 2.86, and 3.02, this is getting close, fall between those numbers. When I do the wavelength calculations using hc over lambda, or hc over E, sorry, the wavelengths, I should have written that formula in too. These are all coming from wavelength equals hc over energy. Now it turns out that if I go from 7 to 2, I'm outside, it takes me just barely outside of visible into the ultraviolet part of the spectrum. So there are only these 4 that fall within visible, and you know, the visible part of the spectrum is a narrow range of energies. And so we're only getting 4 of these transitions showing up. Now, when they ask about UV photons, there are many options here. Now, what I chose to do was just take 2 to 1, 3 to 1, 4 to 1, 5 to 1. Anything dropping into that lowest state is going to be at least 10.2 eV. And then they just get higher. 2 to 1 is right at 10.2. 3 to 1, 4 to 1, 5 to 1, those are even higher energy photons. So these are the energies that we come up with. And then when I calculated the wavelengths using the energies, hc over energy, these are the wavelengths that I got. And see, the wavelengths are getting shorter, the energies are getting larger. And then finally in part C, they are asking about infrared. And I thought, well, for infrared, what could we do? Anything dropping into 2 is either going to be visible or ultraviolet. So nothing dropping into 1, everything dropping into 1 is too much energy for infrared. Everything dropping into state 2 would be too much energy for infrared. So I had to move on to things dropping into 3, and so I just used 4, 5, 6, 7. And those gave me energies well below these numbers. So that's kind of interesting too, that 3 to 2 was within visible, and there's nothing in terms of energies. 4 to 3, 3 is at minus 1.51. I see. Yeah, everything dropping into 3 is going to be infrared. So I just picked these. These are the energies that I came up with. So everything calculated here comes from taking one of these energies and subtracting off one of the others. And then the wavelengths come from taking hc and dividing by the energy. So that was used for all of these. And that takes care of all those transitions. Okay. And again, you can look forward to chapter 39, where we'll come back and we'll do quantum physics the right way. Not all those errors or those flaws that were introduced when Bohr was deriving the formula for energies. We'll come back and show how the energy formulas actually come about. And it's not trivial, and that's why having the Bohr formula is really handy for us. Okay, let's take a break. So this is the first set of problems that we're going to look at today, and that takes us through that first set. Whatever questions you guys have, stop by.